Hello, students. Welcome back. I hope everybody's doing well. I've missed you guys. Yeah, it feels like it's been a long time since we last, quote unquote, saw each other, I guess. But I'm glad so many of you made it back to this session. And honestly, hope you had a good spring break and hope that you guys got to get some stuff done, catch up with things, get some rest. My heart goes out to you if you've been, wrestling with issues in life like work and family and all that kind of stuff. I think, as I mentioned a couple of weeks ago, my son, who works in the hotel industry, got laid off and just found out yesterday that his unemployment application had not been processed. They were asking him to actually snail mail some of the stuff, and so he was very frustrated with that. So, I understand people who are struggling with these things, but I hope you're staying safe and you're healthy. And my heart goes out to you, and hope we can have a good time tonight. Okay. Uh, I guess first thing we have to do is catch up with what's going on. So again, feel free to unmute your microphone if you need to ask a question or something along the way. Okay. But let's go to our Canvas page here briefly. And I'm in the wrong place here. Let me come back here to our home screen. This is what it looks like, more or less. If you're a student, more or less, it's a simulation again. Hopefully you took note that we changed the home page into a more sequential set of topics. And we've posted the revised schedule. So maybe we can go there and look at some things with the revised schedule. All right. So let's go here. Okay, here it is. All right. So this is our revised schedule. So notice that a couple of things are different. One of them is, for example, tonight we are hoping to get you guys to, if you want to, this is just optional. You can meet with us. I'm going to have an extended session after our lecture to go over experiment P11, which is in your lab manual, but to which I added just a brief post-lab section there. All right, so that's one thing. We're going to be doing a similar thing on Thursday. Again, this is completely optional, and you don't have to stay for it, but you are responsible for turning in these assignments, though. So you can do them on your own, or you can come join our session and work at least partially through it. I want to point out very importantly, oh yes, here it is, ladies and gentlemen. Our exam finally is coming up. So because of the break we've had, I figured we'd have a session just to review, all right? But I may have to change that because of timing, but we'll see. The exam will be a week from this Thursday on the 23rd, okay? So the study guide will go up on Canvas. As I mentioned, as I'll show you back in a few moments, now the topics and assignments are all organized on the basis of the units, not on the basis of other things. So be aware of that, okay? So that's what the exam will look like. Okay, I'll have more information about that on Thursday. So I don't want to spend a lot of time on that right now. Okay, let's see. Let's go back here to our Canvas page. Somebody had a question. So yes, Sarah, the lab is due by tonight. So you can do it by yourself or you can join us for our session. But thanks for asking, appreciate that. Let's go back to our Canvas page again and show you what I meant about the organization. So basically what we're doing is we are reorganizing things module by module. And of course, several things have passed already. You know, we had several units, but let me focus on the unit we're in right now. Here it is, Unit 16, Equilibrium and Aqueous Solutions. Here is where you can download the lecture and notes from our last session that we had. I hope you don't mind my, look in there. I'm not that good at things, but you can scroll through here. And this is the activity we're going to be doing tonight. And of course, there's several things, and again, I'll walk you through it if you need help with it, and then you'll submit the assignment sometime before midnight tonight. All right. You have also another activity which will be on Thursday. I don't think it's available yet. Actually, it might be. It is available. There it is. So I'll work on that one with you on Thursday. All right. Quiz number 7 is on buffers. It actually does not cover the stuff we're going to talk about tonight. It's up to what we discussed before spring break. But, you know, it's not going to be available yet. I think it'll be available sometime midnight tonight. So you guys can go ahead and get started on that one. But it is not due until the 19th, which is Sunday. Yeah, so you have plenty of time for that. Similarly with, let's see what else we have here. There is going to be another experiment that's going to be up, and it is available already if you want to get started on it. Realize that the topic of it is actually something we'll begin discussing maybe tonight, but probably not until Thursday. All right. So that's kind of like the way things are organized now. Just wanted you to see that it's all organized in modules. So at some point over the next week, somewhere in here, between units 16 and 17, a new module is going to pop up, and that's going to be our exam module. Okay, there we go. Okay, so let me see if there are any questions. Nothing on the chat room. Again, thanks for joining us today. I'm excited about this. Let me see what else I need to cover before we move on. There's one thing that I was not able to schedule in because I'm still not sure how it's going to work, and that is to set up office hours. As you know, I also have another class, Chem 1A, and we will be able to work on that. Okay. All right. So you know what I just realized? Okay, yeah, I am recording already. So this recording will be available hopefully by tomorrow morning, most likely. I don't think I'll have time to upload it tonight. But we're going to go ahead and get started. All right. The question, Alexa, when will the recording of the last lecture before spring break be posted? I think it's up already, right? Isn't it there? Didn't I just see it there? I think it's up there already. Oh, there it is. That's the one that we did. That should be it, Alexa. So hopefully that answers your question. Cool. All right. Let's come back here, and we're going to start out by doing a little simple exercise here. This is actually in your PowerPoint notes, I believe. And let me see if it's in here. So this is the first one we're going to be doing. So before we broke for spring break, we were talking about buffers. And the major equation that we discussed was called the Henderson-Hasselbalch Equation. And we did a little set of practice exercises. For example, identifying, if I give you a couple of components, you have to be able to determine, do they work as a buffer system or not? Then we also discussed, if I want to build a buffer system of a target pH, what components should I use? And now we're going to work on something very interesting. Unfortunately, I don't have time to discuss this, but you can look it up in your textbook. I think it's in there. And it's the idea that the pH of our blood is very strictly controlled by a buffer system that consists of the bicarbonate ion and the carbonic acid. All right. So let me switch over here. I'm going to switch to our actual fake whiteboard here. And okay, guys, I'm going to give you a warning. Yesterday in my Chem 1A class, this thing was not working very well. It kept getting all blurry and glitchy. So if that happens, don't worry. Anything that I write here, in my handwriting, all of my handwritten notes are going to be posted to Canvas along with the video of the lecture. So if for some reason this thing kind of starts kind of behaving badly, just be aware that's going to be all right. Okay. So So let's go back here and look at this video here. So this is the problem that we're going to be answering right now, okay? The pH of blood plasma. Let me see if I can zoom in a little bit here. Just a little bit. I don't want to mess around with it too much because I'm afraid it's going to start acting up, right? You know what I'm saying? Okay, so remember that the operation here requires us to apply the Henderson-Hasselbalch equation. I kind of abbreviate it as HH, which says that the pH of a buffer system is going to be the pK of the corresponding acid plus the log of the base molarity divided by the acid molarity. And that's kind of like by convention how we set up these systems, right? So in this case, what we need to do is we need to find out what is the pK of this system, okay? So I'm going to let you guys check this out later, but essentially, typically, what we find is the Ka of the particular acid, which in this case, remember, in a conjugate pair, the one that has more hydrogens, that's the acid one. So that's the one we're looking for. Okay, so what is the Ka? And we should be able to find this in your top hat appendix. And hopefully you remember where that is. And there's actually several tables in there. One of them has Ka values. And we find that for carbonic acid is 4.2 times 10 to the minus 7. Don't forget Ka, like all equilibrium constants that we work with, don't have a set of units. We're just kind of unitless. All right. So our pH target is 7.40. And that should be the pK, which would be minus the log of 4.2 times 10 to the minus 7 plus the log of the base over the acid. And of course, in this case, the base would be the concentration of bicarbonate over the concentration of carbonic acid itself. I think I mentioned last time that carbonic acid is actually produced by carbon dioxide in the air dissolving into water. So a similar thing happens in our bodies, you know, as carbon dioxide is produced by different aspects of metabolism, you get some of that carbon dioxide dissolving into the different cell fluids and then into the bloodstream in the form of carbonic acid, which, you know, rapidly begins to ionize into bicarbonate and in its forms, okay? So this would be, now let's do the algebra here. I'm not gonna do the math here because I can't find my calculator. Hopefully I'll find it before the end of the next section here. Okay, so minus the log of this, it's gonna be 6.38. You can check it out in your calculators. And then we don't know what the ratio here is. So we're gonna leave it expressed as the ratio of bicarbonate to carbonic acid, which is what we're trying to solve for, right? So again, we're gonna put this out here, and this is gonna tell me that essentially 7.40 minus 6.38, which is 1.02, would be the log of this ratio here, right? Everybody with me? All right. And so now it's a matter of eliminating the log. So it means we had to elevate, you know, 10 to this exponent here. So 10 to the 1.02. Again, guys, make sure that you kind of like know how to make your calculator do these kinds of calculations. Different calculators are different, but in my calculator, this comes up to be essentially 11. And that should be the ratio of bicarbonate to carbonic acid. So in other words, the blood has a buffer system in which the ratio of bicarbonate ions to carbonic acid is essentially 11 to 1, right? In other words, it's 11 to 1 ratio of base to acid, right? So the question they asked us here is, so that's the ratio. Again, we're not being asked to calculate what is the actual molarity of these things because they're going to fluctuate according to metabolism. The idea of the buffer system is to handle, any change in acidity that might be produced by any different kinds of metabolisms, whether, maybe your body is in fasting mode, maybe your body is trying to digest a succulent, in and out meal of, with a lot of greasy stuff, right? Or maybe it's trying to process a lot of metabolism of, a lot of greens and seeds and some of that stuff, it depends. So the actual molarity of these things is not the issue, it's the ratio. So the question now I ask you is, does it look like this buffer would be more effective against added acid or against added base? Let me give you a few seconds to think about that. Remember, if I challenge the system with acid, the base component responds. If I challenge the system with extra base, then the acid component of the buffer system responds. So which one is it here? The base, right? Because that's the ones that's present in the, greater amount. So in other words, the system is designed to respond, to be more effective against, and let's say overload or extra or attack of acid, right? So let's say more effective against extra acid. Now, if you ever get a chance to do a class in biochemistry, or if you decide to change majors and end up having to take the Chem 3 class where they go through metabolism and stuff, or if you read on your own, you'll realize that a lot of metabolism tends to produce acidic substances more often than basic substances. The basic substances of metabolism are usually nitrogen-containing bases, which are handled by a different system and essentially eventually excreted through the urine. But in terms of other types of metabolism, like carbohydrates, fats, and stuff like that, protein, and some of protein metabolism, it tends to generate more acid substances than basic substances. So the system in the blood is perfectly designed to handle that, all right? Okay, so like I said, I will have this sheet ready for you later on. I'll scan it and post it to Canvas, okay? Let me know if there's any questions, either on your chat or you can unmute your microphone and ask. Okay, no? All right, let's come back here then. Back to yours truly. There I am. Hey, hello, I'm back. Okay, let's go back to our PowerPoint, and we're gonna, this is gonna be like our closing of the buffers discussion, although tonight, if you wanna join in that optional, guided activity, we'll talk some more about it. And then on Thursday, we're gonna do a really interesting activity. Again, you can do it on your own or you can join us. We're gonna ask the question, well, what happens if I have one of the components of the buffer system, let's say the acid or the base, but I don't have the conjugate? Is there a way of generating it inside or in situ to get the buffer that I want anyway, even though I don't have one of the components available? Okay, so we'll talk about that. Okay, let's go back to our PowerPoint here. I forgot where I was. There we go. Excellent. So I'm going to skip this next section here because, oh, actually, no, I'm sorry. The section I skipped, I think, was before that one. Okay, let's talk about titration. You guys love this word, don't you? That's right. I even used to have a rap about it. I'm looking for a good titration, acid-base neutralization, something like that. Forget it. forget, I'll erase that from the recording, don't worry. So in a titration, what you do is a solution of accurately known concentration is added gradually to another solution of unknown concentration until the chemical reaction between the two solutions is complete, right? So you all remember that what you try to shoot for is what's called the equivalence point, the point at which the reaction is complete. But in many cases, you cannot identify that equivalence point visually or at the macroscopic level. So what we do is we put an indicator, a substance that changes color, near the equivalence point, somewhere around there. And remember the equipment we do, sorry, that's kind of a small picture there, but you have our typical burette being dripped into a reaction flask. There's the little dropper bottle of indicator and then some rinse bottle of water to make sure that you're rinsing the sides of the flask, make sure you get the reaction to go. And let's say in this case, I have an acid solution in the flask with the indicator. I'm going to slowly add the base until I get a very, very faint change of color. Again, not sure if on your screen you can see these colors very well converted, but again, you have hopefully in your handouts, you can see it. So you're going to do this until the indicator changes color. This indicator in particular goes to a faint pink, and we call that the endpoint, remember? So remember that the endpoint is not the same as the equivalence point. It's just close to it, but it is typically within the range of error that we typically get in a titration experiment, okay? Now, tonight I'm going to show you a different way of following the titration of a substance, and that is by monitoring the pH as you do the reaction. Notice that in this case, the reaction is being carried out not in a flask, but in a beaker, and that's to give you enough space to stick in that probe there, which is attached to a pH meter. Now, the pH meter you're seeing here is pretty bulky. What we do nowadays in labs is we have two options. One is the one that you would have used if you had been in lab, which is kind of like a handheld pH meter that has kind of like a little bigger than a marker or something like that. It's kind of like, we call it a pen, but they're a little bigger than a pen. And the other possibility is to have an actual probe that attaches to your computer and to a program in it, so it graphs out the progress of the titration. All right. So we're going to be doing some pretend pH measurements in tonight's, optional lab activity, and then some more in Thursday's lab activity. Now, I want you guys to be reminded of how titration calculations work. So let's do a quick review of how to do a titration, right? So let's say it takes 25.00 milliliters of 0.100 molar NaOH to titrate 5.00 milliliters of an HCl solution. What is the molarity of the HCl? And I'm going to add a question. What is the pH of the final reaction mixture? Okay, so remember the way we do this is we look at the reaction, make sure we have the stoichiometry right? So that's our reaction, NaOH reacting with HCl. And the products are, of course, water and the salt solution of the conjugates. Of course, in this case, sodium and chloride, as we say, we might call them conjugates, but it's kind of like a kind of a no-brainer that they're not going to be really conjugate pairs. We can also look at the net ionic equation, which pretty much for any reaction in aqueous medium like this is going to be hydroxide ions reacting with hydrogen ions to produce water. Okay, so let's go to our screen here, and hopefully some of you are already working on it, right? So let's go over here to our screen, and let's see if we remember how to do these kinds of calculations, okay? Now, I know some people typically use the, remember the dilution formula, M1 V1 equals M2 V2? Remember that that is only true if the number of moles of each substance is the same, which in this case, it's okay. right? In this case, the number of moles of HCl should equal the number of moles of hydroxide ion because they are reacting in a 1-to-1 ratio, but that is not always the case. So I prefer that students do this the old-fashioned way, which is stoichiometry. So I have 25 milliliters of NaOH, which is 0.100 molar, which means there's 0.100 moles of NaOH per liter. But since I want to cancel out milliliters, I'm going to write this as 1,000 mLs. And the reaction says that I am going to get 1 mole of HCl for every mole of NaOH. And let me close this shade here. It's got a beam of light coming in through there. There you go. Right? So that is going to tell me how many moles of HCl I had, right? And then what's going to happen is I'm going to have in here all of that divided by the milliliters, which is 5 milliliters of HCl solution, which, remember that 1 liter of HCl is 1,000 mLs, right? Now, if you kind of like remember how to do these things, you probably didn't even need to do these calculations because you know basically that since they react 1-to-1, if you have 0.1 molar of this and it takes 5 times the volume of HCl, it must mean that the HCl is 5 times as concentrated, right? So basically, this is going to end up looking like 0.500 molar HCl. All right. Okay, so I did that just to make sure you guys remember how to do titrations, right? Just in case you are asked about it in an upcoming lab. Hint, hint. All right, there we go. Okay, now the question they asked you after this was, what is the pH of the final reaction mixture? What is the pH at the end? So let's do this. Let's come back here to our PowerPoint and continue this discussion. Okay. Okay, so what is the pH of the solution? Well, think about it. What is the product of this reaction? Remember, the products are essentially a salt solution where both the cation and the anion are the conjugates, quote unquote, of a strong base and a strong acid. In other words, there is no hydrolysis by this salt. And the other product is just water. In other words, what you have here is a neutral solution, correct? This should be completely, let's see if I can get this thing to work. Oops, sorry. I can't get it to work. Well, I'm trying to put there neutral, but today my stylus is not working too well. Sorry about that. All right, let's go back here. So the thing that we did though in this experiment was that instead of simply adding base from a burette and then measuring the initial and final volumes, we added it gradually, and as the reaction, the titration proceeded, we recorded the pH after each, let's say 10 drops or something like that. And what you get is a curve that looks like this. Notice that it's an S-shaped curve. Notice that you start out, right, with a acid solution. And after you have stepped over the titration, the equivalence point, you have a basic solution there. So a couple of things about this. First of all, notice that the curve has a very, very steep rise right around the equivalence point. How do I know what the equivalence point is from this graph? Well, what I do is I look, first of all, I draw a line in the bottom, and I draw a line in the top, and I ask, what is the midpoint of this? Let me see if I can try my pen again. What is the midpoint here? All right, that's what I'm looking for. And that midpoint is going to tell me how many milliliters of NaOH were required. You can see here on the table in here, that's your result. Remember we said it was going to take 25 milliliters to do it? Well, notice that this is a different way. In this case, what you do is you look for the halfway point between all acid and all base, because at that point, essentially, that is where you're about to kick over from an acidic solution into an entirely basic solution. Notice how sharp that rise is, and answer the question, why is it so easy when I do a titration with an indicator to overshoot it? Well, you can see how a very, very small change in volume of NaOH causes a dramatic increase in the pH. And therefore, your indicator is ready to pop right there, all right? So you can see that how it works. Now, what we notice here is, just like we said, because the solution is neutral at the equivalence point, because the product at the equivalence point is simply water and a salt solution, the pH is 7. In other words, this is a neutral solution, all right? Now, what would happen if instead of a strong acid, strong base titration, what if I did it with rather a, oops, I'm sorry, I'm going the wrong way. Sorry about that. What if I went with a weak acid? For example, let's say acetic acid, which you've seen the formula before, right? Okay, again, if I were to look at the reaction, again, strong base, NaOH, products are the salt of sodium and the acetate ion and water. Let's look at the net ionic equation here. This is the reaction of the acid with the hydroxide ions. And the important thing here is to look at our product. Our product is the conjugate base of a weak acid. Therefore, at the equivalence point, in other words, when all of the acid has reacted and has been converted into this conjugate base, that conjugate base is going to hydrolyze. In other words, it is going to itself behave as a weak base and generate hydroxide ions in solution, which means that at this point, the pH of the solution is not neutral. It's actually going to be slightly basic or alkaline, which is the other word we use for that. If we monitor this titration with a pH meter and do the graph we did before, we notice some differences, right? Similarly, though, it is S-shaped. However, one difference is that the initial portion of the graph starts out increasing in pH and then kind of levels off for a little while. And we'll talk about that on Thursday in our activity. But just to give you a heads up, basically what it means is as a conjugate base is being produced by the titration, the conjugate base and the acid are forming a, a buffer system and resisting the increase in pH caused by the NaOH. Of course, at some point, the NaOH essentially overtakes it. The curve starts rising. And just like before, the way we do it is we run a horizontal line there. Sorry, that's about as horizontal as I can get it. And then another one over here, right? And we look for the half point, the midpoint there. And that should tell us what is the volume of NaOH required to reach the equivalence point. In other words, for titration. We can still use that value just like we did before. In this case, again, notice that it's, again, 25.0 milliliters. So if this was a 0.5 molar acid, that's what it took. But notice the difference is that the pH now came up positive. In other words, it's a slightly basic solution, and that is because of the, again, like I said, the hydrolysis caused by the conjugate base product of the titration. Okay, so hopefully everybody understands that. What I'm going to do now is we're going to walk ourselves through a set of calculations, but let's do this. Let's see if there's any questions. Jennifer, the number of moles aren't the same. Can we still use the M1V1, M2V2 equation? Yes, you have to adjust by the number of moles. For example, if you're doing sulfuric acid, that means you would have to have 2 moles of base for every mole of acid. So you'd have to adjust it that way. And as long as you remember to adjust for the stoichiometry, it's okay to use this formula. I like the dimensional analysis method and pathway because to me it's more consistent with other types of reactions that we study. Okay, let's do this. Let's take a 10-minute break. And then when we come back, we're going to do a long practice problem. All right. So let's take a 10-minute break. Okay, we are back. Hope you had a little bit of a rest there. Maybe you got something to eat or drink or something like that. Again, I don't know what your surroundings are like. And hold on a second. Let me close those shades a little more. I got one. I look like a half moon with bright side and the dark side here. So anyway, again, I don't know what your surroundings are like, and I realize some of you might be having to compete in your house for room and freedom of noise with other family members. So again, hopefully the recordings of the lectures will help you to fill in any gaps, anything that you missed. Okay. All right. So let's come back here to our discussion about titrations. And here is the exercise that we're going to do next. Okay. This is going to take a little while here. I'll take most of the rest of the session here. So let's say that exactly 100 milliliters of 0.100 molar HNO2, and you might not remember what that is, but it's called nitrous acid, are titrated with a 0.100 molar NaOH solution. What is the pH? A, of the initial solution. B, after addition of exactly 80 milliliters of base. C, at the equivalence point. And D, after addition of exactly 105 milliliters of base. All right. Right, we're going to take this step by step. I'm going to bring us back here to our makeshift whiteboard. And there it is. Oh, there we go. So we're going to take it one step at a time. All right. So there are various strategies of how to solve these kind of problems. I'm going to walk you through one. After you've done a few practice problems, you'll probably end up coming up with your own version of these. But for the moment, let's make sure that we get this. Let me make sure my audio is working. Yeah. And let's make sure that this is okay. All right, here we go. So let's start out with A. the initial solution. Well, as you know, what you have is a solution of HNO2. And HNO2 is a weak acid, right? So it will partially ionize into hydrogen ions and the conjugate base, which is the nitrite ion. And we're going to set up our ice table. We're starting out at 0.100 molar. We're going to use molarities here. And of course, none of the products of ionization. We will do our typical change. And once more, I'm going to use the letter Y instead of X. And then we'll see what happens at equilibrium. So at 0.100 minus Y, Y, and Y. Okay, so as usual, we do an approximation to start with, right? So let's start with our oh, I lost track of letters here. Okay, sorry, approximation. Oh, gosh. Sorry, guys. Approximation. So we would say that the Ka, which is, according to this, 4.6 times 10 to the negative 4, would be y squared over 0.100 minus y, just like we've done before. And we're going to say that this could be assumed to not show a significant change in the concentration of the unionized acid. So we're going to solve this. So y is going to be square root of 0.100, right, times 4.6 times 10 to the minus 4. And I believe that is 6.8 times 10 to the negative 3. All right. I kind of like skipped a few operations here, but that should work more or less. Now we're going to test our approximation. And it's going to turn out that 6.8 times 10 to the negative 3 divided by the initial molarity 0.1 gives you a number that is essentially 6.8%. In other words, approximation didn't work. So guess what we got to do? We got to go quadratic. That's right. And I know that you guys love this. I kind of did it on purpose to make you guys work your way through it. But essentially, we got to come in here and go quadratic. So I'm going to go ahead and display here what the equation looks like. Oops, sorry, I forgot to close this parenthesis here. Sorry about that. And what it's going to turn up to be will be y squared plus 4.6 times 10 to the minus 4 times y minus 4.6 times 10 to the minus 5. Again, I'm skipping all the algebra manipulations here. Hopefully you can either trust me or do it yourselves very quick. So that's 0. And remember that in our format here, we would say A equals 1, B equals 4.6 times 10 to the minus 4. C, careful with the sign, is minus 4.6 times 10 to the minus 5. And we said that the solution of our equation is minus B plus or minus square root of b squared minus 4ac over 2a. Oops. Let me get this up here a little bit. There you go. Oops. There. Okay. So now you have to plug numbers in, and let me show you something I did. I just sorry. I'm going to cheat here, okay? Let me show you something that I have. So a few years ago, I decided, you know what, I don't want to be doing this stuff. So I'm going to set up a spreadsheet. And here it is. And what I do is I simply plug in the Ka over here. So what was ours? 4.6 to the minus 4, right? And then I put in here the molarity of the acid. And see, that's the approximate, the worksheet is going to calculate everything here. So 6.8 times 10 to the negative 3 gives me a 6.8% test. So that's not going to work. So what this is going to do, as you can see, it already came up with what were the proper coefficients here, A, B, and C. And over here is going to give me the two possible solutions. Now I got to choose which one I want, and one of them is negative, so I'm eliminating it. And so I'm going to choose here which one it is. So since in this case, the approximation didn't work, what I'm going to put in here is going to be this number here that I got here. 6.6 times 10 to the negative 3. All right. Guys, se vale, no? It's you can build something like this. You can probably even do it on your calculator, or your if you have a graphing calculator, you can set this up for a quadratic equation. If you have an iPad or iPhone, you can download the Excel app and do it there, or you can do it in your own thing. Now, if you guys want, I can share it with you later on if you want. But the cool thing is that not only does it do that, but it also gives me the pH 2.18. So basically, coming back here to our screen cam here, let's come back in here. We found out that the solution of the equation was y equals 6.6 times 10 to the minus 3. And we know that that is the molarity of H plus. So pH, we said, was going to be 2.18. All right. So I'm going to put a little parenthesis here. You can use Excel or graphing calculator. I'm going to let you do that. Don't forget, when you take the exam, I'm not going to be monitoring what tools you use. So if you want to use that, that's fine with me. This is not a math class. So as long as you get to the right answer, more power to you. But if you want to really practice, you'll have to work this out and have to be very careful with your operations. And of course, very careful with that negative sign on the third term of the quadratic equation. Okay, so took care of A, which was what is the pH of the initial solution. Okay, cool. Now let's do the second one. Here we go. Now we're going to do, pull this out, let's pull it in again. There we go. B. What happens after the addition of exactly 80 milliliters of base? Remember, when we say exactly, it means, put in as many decimals as, a typical instrument can deliver. Since this is a titration, we would expect this to have been a burette, and the milliliters delivered would be in 2 decimal places. So just be careful with that, okay? So again, we are going to be needing to build again, a ice table. So let's go back again. But remember, the issue here is HNO2 now is not alone. It's actually reacting with base. I'm going to look at just the net equation here. And this is going to generate, of course, it's going to neutralize a certain amount of the acid. We can tell because of the relative molarities being the same and the volume of NaOH being less than what it is for the acid, that you have not fully titrated the acid yet. So, and this is going to be H2O. So the question now is, what are we starting at? Well, be careful, because at this point you have diluted your solution. So your concentrations are not the initial concentrations of either one, okay? So let's go ahead over here and calculate what these are. So let's see, what is the concentration of the acid after adding 80 milliliters of base? Again, we use the dilution formula, so we started out with 0.100 molar. All right. We had 100 exactly milliliters of that. And the final volume is going to be, oops, this is not brackets, I'm sorry. These parentheses here. 100 plus 80. Because that's how much we added. So that cancels out the milliliters. And we can calculate our new molarity here. All right. So you're diluting, essentially 100 moles into 100 and 0.180. You got a dilution here. So this is going to be 5.56 times 10 to the negative 2 molar. Or you can write it if you want in decimals if you want. So 0.0556. It's not quite a 1-to-1 dilution, so you don't end up with 0.05 molar. Okay, let's see what it's going to be for the hydroxide ion concentration. So this solution is similarly 0.100 molar, but we are adding 80 milliliters. And that's going to be diluted into 100 plus 80 mLs. And this is going to be, again, I'm skipping the calculations here, guys. 4.44 times 10 to the minus 2 molar. Which would then make this guy here 0.0444 molar. And of course, in our initial conditions, we're still not reacted. Now, remember, in this case, the hydroxide ion is going from a strong base, so all of it should react, right? Since it's in, the limiting amount to the acid, they are going to react in a 1-to-1 ratio and therefore generate that molarity of nitrite ions, so that at the end of the process, we have the difference between these two, which is 0.0112 molar, no hydroxide ions left, and 0.0444 molar in the conjugate base. Give me a few seconds to kind of work your way through that one. Just make sure everybody's kind of like on board. Okay, again, repeating, this is not an equilibrium process. We are, reacting. a portion of the acid with a strong base and generating a mixture that now has some leftover acid and the conjugate base. All of the hydroxide has to react. We just had to adjust the concentrations for the dilution of the both solutions as they got mixed. Okay, now, again, what I have now is a solution that has some of the acid and some of the conjugate base. What do we call that? Right, we have here essentially a buffer solution. So what we're going to do is we're going to use the Henderson-Hasselbalch equation. So the pH of this solution would be pKa plus the log of base, which is nitrite ions, over acid, which is the HNO2, right? Everybody with me? Okay, what was the pKa? Well, the pKa would be minus the log of this number here, 4.6 times 10 to the minus 4, right? You know what? I lost my notes, so I'm going to have to do it here. We'll do it together. 4.6 to the minus 4. We do the log minus that, 3.337. So since we have two sig figs in our input number, we have to have two decimals. So this is going to be 3.34. And this is what we call the pKa. All right. So back to our equation here, the pH is going to be 3.34 plus the log of. Okay, we calculated the concentrations of both components after the addition of the extra base. So the base is 0.0444 divided by 0.0112. And again, you can see where the ratio of base to acid is bigger than 1. That means that the logarithm here is going to be a positive number. So that means that the pH is going to be a little higher than the pK, right? Because that's the way it works. So if you want to do that, let's say we're going to have 0.0444 divided by 0.0112. Yeah, bigger than 1. We're going to take the log of that. It gives us a positive number. And we're going to add it to our pK, 3.34. And that gives us 3.938, which we now have to round to 2 decimals. So it comes out to be 3.94. And that is the pH of the solution. So remember, the solution started at 2.18 pH. You have nearly added, you're like 4/5 of the way to neutralizing all your acid, and your pH has barely risen less than 2 units, which means less than 100-fold decrease in your hydrogen ion concentration. That's pretty good, because remember, during this stage of the titration, the acid and base that are produced, the acid and its conjugate base that is being produced are acting as a buffer system resisting pH change. Well, it's not going to last very long, because we're going to work now on what happens at the equivalence point. Okay, let me give you a few more seconds to write that down. All right, let's take it out. Now let's go to stage C. What is going to happen at the equivalence point? You know what? Remember, chemistry before math, all right? what is happening at the equivalence point? Let's talk chemical before we do any math. By definition, what it says is that your reaction is complete, right? In other words, all the acid has reacted. Secondly, because the NaOH had the same molarity as the HNO2, that means that it should have taken the same volume of NaOH solution to titrate that. So it should have taken, or it would have taken, I keep talking like my wife sometimes, not would, but it would have taken 100 mLs of the NaOH solution. And thirdly, all the original acid is now the conjugate base. That's now, sorry. All right. So what is going to affect the pH of this solution? Remember, the solution is not going to be neutral because that conjugate base, that product of the complete reaction of the acid, is now going to hydrolyze, right? So the NO2 is going to hydrolyze in water to give us some acid back and hydroxide ions. So let's see what our molarities are. Well, again, we have to do some calculations, right? So the new molarity of NO2 is 0.100 molar. You know what? Let me do this. Let me do it up here. Sorry for the lack of space. So it started out at this being 0.10 molar. Remember the initial concentration. And you had used exactly 100 milliliters of that solution. Now that was the moles of acid, which is now moles of base. And the new molarity would be, I'm sorry, the new volume would be 100 of the initial solution plus 100 of the new one. So all you're doing basically here is you're diluting this guy to 1/2, right? I mean, you can do it in your head even if you want. So this has got now 0.0500 molar, all right? So let's write that in here. Okay, let's complete our I state. Some of it is going to react here. And again, you can use Y, you can use Z. I sometimes use Z for this one, or Z. So that once the equilibrium is established, you have 0.0500 minus Z. And then you have Z acid being produced back again, and then Z ions of hydroxide. So we need to solve here. But the thing here is that Kb here is the constant. This is a base equilibrium, not an acid equilibrium. And they didn't give us the value of that, so we're going to have to calculate it. And we learned that the way you do that is divide the Kw by the Ka. So that's Kw is a constant, and the Ka we said was 4.6 times 10 to the minus 4. And this ends up being, when you round it up, 2.2 times 10 to the minus 11. Because as weak as an acid, as nitrous acid is, its conjugate base is even weaker as a base. All right, so Kb, which is 2.2 times 10 to the negative 11, should be C squared times this difference here. Again, we're going to try the approximation to start with, right? So Z squared over 0.0500. It's pretty safe with that small a value of Kb in this case. It's pretty safe to assume this is going to work out, right? All right. So Z is going to be the square root of 0.500 times 2.2 times 10 to the negative 11. I mean, we can do the calculation if you guys want. 2.2 minus 11 times 0.050 equals that. Square root is 1.04 times 10 to the negative 6. All right. Is that right? So yeah, let's say then this is about 1.0 times 10 to the minus 6. You know what? Actually, no, we have to, yeah, let's call it that way. Now, remember, according to our, oops, let me get this calculator out of the way. This would be the concentration of hydroxide ions. We're looking for the concentration of hydrogen ions. So one way we could do this is we could say, well, pH equals 14 minus the pOH. In other words, 14 minus the negative of the log of 1.0 times 10 to the minus 6, right? And what did you guys get from there? Gosh, I can't get this thing to squeeze. There you go. All right, so we had that number there. So we take the log of that, and we take the negative of that. But since we have a double negative, right, we're going to be adding, subtracting this directly from 14. So I'm going to put that in there, and then I'm going to say 14 minus the pOH, 8.0206. So 8.02. As predicted, the pH at the equivalence point is not 7. It's slightly basic because the product of the titration, the nitrite ion, is a weak base that hydrolyzes to increase the concentration of hydroxide ions above neutrality. And that's why you have a higher pH. Okay, a few more moments to let you guys absorb that. And then we'll tackle the last step here, which is after the addition of exactly 105 milliliters of base. Let me know if you have any questions. You can unmute your phone, your microphone if you want. Ask. Sorry. Kind of losing my voice a little bit here, so I gotta give it a break. Okay, so let's go to the last one here. So our last exercise here is what happens after the addition of exactly 105 milliliters of base, right? So remember, at this point, you're past the equivalence point. In other words, what you have here is you have an excess, right, of moles of, OH minus, right? So here's two things. You have a little excess of OH minus and some of the nitrite ion, right? Because remember that it got produced, it's in there, it's kind of hydrolyzing. However, because the nitrite ion is weak, it's not going to contribute significantly to the concentration of hydroxide ions in there, right? Small, negligible contribution to the total molarity of hydroxide ions. Remember, you think chemistry before you think math, all right? So essentially what we're saying at this point is that the pH is going to be determined essentially by the molarity of the the NaOH essentially, right? So let's see. How do I want to do this? We can do this several ways. So we can say that the molarity of hydroxide ions is going to be, right? So you have basically the moles left over divided by the final volume. Okay, so basically you needed essentially, if you had added 105 milliliters, right? Of a solution that was 0.100 molar. And you had to, some of that got reacted, right? We said that essentially 100 milliliters of that was used to react with the acid. Right? So this is added. And this is the reacted. Right? And then we're going to divide final volume, which would be 100 milliliters that you started with of acid and base. Of acid plus 105 milliliters of the base added. All right. So essentially, what you have is on the top, you have 105 minus 100, that's 5 milliliters times 0.1 moles per liter divided by 205 milliliters. So that's about 2.4 times 10 to the 2.44 Let's see, we can have 3 sig figs here, right? So this will be 2.44 times 10 to the negative 3 molar. So that is the concentration here. And now we're going to calculate the pH. So again, 14 minus negative of the log of 2.44 times 10 to the minus 3. All right, so let's see what that is. We got the log of this, got the negative of it, and then it's going to be 14 minus that, so I'm just going to put the negative again here. Plus 14, so I get 11.387. We got 3 sig figs here, that'd be 2 sides, but we only use 2 typically, so I'm going to put it 1139. All right, and that's what happens at this stage. So notice how from the equivalence point that was at pH 8 to, just 5 milliliters beyond that, bang, it shot up to, almost 11.5 pH. 2.5, 3.5 pH units, right? 3.5 pH units. In other words, 3.5 powers of 10 increase in OH minus concentration versus what it was at the equivalence point. So you can remember how that graph, when you look at that graph, that's such a steep rising part of it. All right. So again, the way it would have looked like, it would have been something like, if this was the milliliters of NaOH, and this was the pH, it would have started somewhere around pH 2, increase slightly, then kind of level off, and then kind of go up, and then kind of level off again. And at your equivalence point, it would have been about pH 8, more or less. All right. Cool. Again, you're going to get all these sheets scanned and placed in your Canvas module where the lecture video is going to be. Okay. So let me see if there are any questions. I'm going to open the chat room just in case somebody missed this. No, we're good. Okay, so it sounds like a lot of math, a lot of stuff, and yes, it is, but I hope that beyond the math, you can think about how we looked at each stage in this process, right? I think that's very important that you remember that. It's not just about the math, it's about, applying what you've learned about the process by which an acid and a base react, and the difference when a strong base and a strong acid react, which is all pretty straightforward, versus a weak acid that would be generating a conjugate base that then hydrolyzes, okay? So let's make sure that we get that, okay? Okay, let's wrap it up by looking at a couple more things, but we're not going to do a lot of practice now from here on out. You guys have had enough practice here for today. All right, so we did this. I wanted you to think about the opposite process here, and that is what happens if instead of titrating a weak acid, I titrate a weak base, all right? So for example, let's say that I'm titrating ammonia with HCl, right? Once more, if we look at the net ionic equation, we're titrating essentially ammonia with hydrogen ions to produce ammonium ions. The chloride ion is essentially a spectator. Now, here's the thing. That product that we see there, right? That product is itself a weak acid. And so at the equivalence point, when all the ammonia has been converted into that ammonium ion, you're going to have the ammonium ion hydrolyzing to produce a solution that has a pH lower than 7. In other words, it's acidic because it's producing additional hydrogen ions. Once more, if we look at the graph, if we follow the titration by pH, instead of simply with a color indicator to find the equivalence point or endpoint in that case, we find this kind of like a reverse S-shaped curve. Once more, look at how it kind of starts out lowering in pH and kind of like evens off for a little while there. That's the buffering activity of the ammonia and ammonium ions. And then it drops again very rapidly around the equivalence point, which again would be calculated by looking at what's the maximum and minimum here and finding essentially the half point of that and then tracking it down here to what is the volume. But notice how the pH at that point is slightly acidic because of the action of the ammonium ion. Okay, I have a problem here for us to solve, but we've taken up enough time. So we can do this one if you want. We can do it Thursday night in our extra session for those of you who want to. I will record it anyway, so you'll have access to it if you want. But I'd rather just go ahead and wrap it up here by looking at this idea of the acid-base indicators. Remember that we said that an indicator is a substance that changes color right around where the equivalence point is for the acid-base reaction. So essentially, because the indicator is present in a smaller amount, it doesn't react immediately with the incoming base, your titrant of base. And so it takes a little while until right after the acid has been totally neutralized. And at that point, then there is leftover base for the indicator to react with. So essentially what we're saying is that the indicator itself is a weak acid. So if we represent it this way as HIN, you can see where it's going to be in an equilibrium where it produces, hydrogen ions and then its conjugate base, right? So let's say that we apply the Henderson-Hasselbalch equation to this equilibrium. We would say that the pH would be the pK plus the log of the base over the acid. In this case, right, the so-called conjugate base would be, let me write it down here, would be the IN and the acid would be H IN. So essentially, what we're asking is, at what pH are we going to see a dramatic change in the balance, in the ratio between these two forms? Remember, the idea is that either the acid form or the base form have different colors, or one of them is colorless and the other one has a color. So essentially what we say is, let's consider a situation where the ratio of the indicator base to the indicator acid form is 10 or more. In other words, like one exponent of 10, 1 power of 10. Then if that's the case, then that means that the pH is going to be pK plus 1. So it's going to be slightly to the basic side, which means that the color of the conjugate base is going to be the predominant one. So let's say that the base is blue and the acid is yellow. Well, at 1, essentially what we're saying is that at a ratio of 10 times of base to acid, you're going to have a pH that's 1 unit more than the pK. If, on the other hand, the ratio is less than 10, right? Well, that means, therefore, that you're going to have a 1 in 10 there, so it's going to be less than the pH, so it's going to be pK minus 1. And in that case, the acid form of the indicator predominates, so whatever color that is, that's what you're going to see in the solution. So why am I showing these things? Well, the idea here is that when we're doing a titration with an indicator, you want to choose an indicator that changes colors essentially at plus or minus 1 pH unit from the pK of that acid, right? That's what we're looking for. We're going to try to see if we know what the predicted equivalence point is, we want to try to get an indicator that will experience its color change within 1 pH unit of that equivalence point, all right? So here is a table that shows us a bunch of these indicators, and you'll recognize maybe at least one of them there, which is the phenolphthalein. Notice that phenolphthalein is very useful because it doesn't change. Like most of these guys have 2 different colors, some of them 3 colors, some of them 4 colors. Phenolphthalein is very easy because it goes from colorless to pink. It's a very easy color change to spot. Notice that it does it at a pK somewhere around at a pH somewhere around the basic side, right above 8 going towards 9. So that is an ideal indicator to use when you're titrating a strong acid with a strong base, because what it says is that it's going to essentially, since the equivalence point of that titration is going to be around pH 7, as we saw before, the indicator is going to change very quickly right after that. So it's a very good indicator to use. Notice that other indicators that fall in the more acid pH range, like thymol blue, or let's say bromphenols blue, all of these guys will basically try to change before the acid-base titration has reached the equivalence point. So it's probably not, they're not good choices, all right? So let's do some exercises. Look at this titration curve. Okay, this is a strong acid with a strong base. Remember, this is the same one we did before. Notice that at the equivalence point, which we said was going to be at 25 milliliters, the pH should be set. Notice that both methyl red and thymol blue will change colors before the system arrives at the equivalence point. So it's kind of a little tricky because, for example, with the methyl red, you're going to change from a red color to a yellowish color before you reach the equivalence point. You would prefer phenolphthalein because it changes right after the equivalence point. Now, this is the sharp rising part of the graph. So, technically it's not that big a deal. You could use the methyl red. From experience, I'll tell you, I like a color change that goes from colorless to color, as opposed to from red through orange through yellow, and try to kind of pinpoint exactly where this thing is, all right? So let's do a little few exercises here, have you guys practice. For example, let's say I'm going to titrate nitric acid, right, with NaOH. Which indicators would be good for this? Okay, remember, this is a strong acid, and you know that because you've memorized them already, with a strong base. So at the equivalence point, the products are not going to have hydrolysis. You're going to have essentially sodium nitrate and water. At the equivalence point, the pH is going to be 7. So what we would like to do is find an indicator that will change, somewhere around where the equivalence point is going to happen. All right. So I would say any one of these last 3 here might work. Bromothionyl blue, kind of a little bit sketchy, but cresol red and phenolphthalein definitely would work because they're going to change colors right around where the equivalence point is going to happen, which is pH 7. Okay, guys, so I would say any one of these 3, bromothionyl blue, so I misspelled it as bromothionyl blue, or cresol red, or phenolphthalein. And of course, you guys have used phenolphthalein extensively. That's the one we typically use, right? Okay, let's try another one. Let's try titration with HNO2. All right, it's not in that list, so that means that you're talking about a weak acid titrated with a strong base. So that means that when we reach the equivalence point, all of that acid has been converted into a conjugate base, right? The NO2 minus, we just did a long exercise talking about this. So that means that that conjugate base will hydrolyze right? And so at the equivalence point, the pH goes above 7. So now you have to decide, okay, so which indicator am I going to use? Let's look at this list here. Notice that it's going to show you the pH ranges. Notice also that of all these guys here, the only one that goes from colorless to a color is phenolphthalein. Everything else goes from one color to another one, right? Either yellow to red or yellow to blue or red to yellow or orange to yellow. But here, what you have is, notice that in this case, the bromothionyl blue will have changed colors before you reach that high pH, which will probably be around 8 or so. So in this case, I would say the ones that work would be just the bottom two. Cresol red, just kind of right in there. And of course, phenolphthalein still works because it changes colors at a pH higher than 8, which is pretty close to the equivalence point. So you should be able to use it, right? Okay. And I know we haven't done any practice exercises with it, but how about if we're titrating a base with an acid? That works too, right? Let's say we have this substance here, CH3NH2 with HBr. All right, so you don't know what CH3NH2 is, but you know what HBr is, hydrobromic acid. It is a strong acid. So because a titration requires an acid and a base, that must mean that CH3NH2 is the base. And perhaps by now you realize that all of these nitrogen-containing bases are weak bases. So this is a weak base titrated with a strong acid. Remember that this is going to be a curve that's going to go downward. It's going to start at a high pH, and it's going to slope down and very rapidly decrease around the equivalence point until it settles at a lower pH when you have the excess acid, right? So at the equivalence point, this base is going to generate a conjugate acid, and that conjugate acid is going to hydrolyze. So that means that you're going to have, at the equivalence point, a pH that is less than 7. It's going to be acidic. So what you would like to do is you would like to catch the equivalence point with an indicator that changes colors just slightly past that acidic pH. Again, like I said, we didn't do the practice exercise, but I think I showed you the one with the ammonia being titrated and how the pH at the equivalence point was like something like 5 point something. So that's what you're looking at. You're looking at something that's going to be in the pH 5 to pH 6 kind of range when it reaches the equivalence point. So let's look at some of the candidates here. You can see that phenolphthalein wouldn't work here because by the time the system reaches that sloping down, that fast sloping down portion of that titration curve, phenolphthalein will have already turned pink. So it's kind of like a tricky one. Okay, so you probably are guessing right now, yeah, we would look for some of these guys here. Notice that the first one, thymol blue, bromophenol blue, those tend to change colors at a very, very low pH. So, you know, by the time they change, you will be pretty well past the equivalence point. So they're probably not a good choice. So it looks like to me in this one here, the ranges for methyl red and chlorophenol blue are probably ideal. They're somewhere right where you want them to be. So maybe those two would work, right? What do you guys think? Cool? Thumbs up? Yeah. Okay, guys, I think that's all that we have for today. That's been plenty, right? So let's come back here to Dr. DA. So, okay, so pretty much that concludes our study of acid and base equilibrium. Going back to the previous unit, chapter 15, and pretty much halfway through this chapter 16, our next topic is going to be solubility equilibrium. So we will tackle that on Thursday, all right? And then we're going to have a guided lab activity for you that you'll do over the weekend, where we calculate the equilibrium constant for a solubility equilibrium. It's called the solubility product, or KSP. So we will discuss all that stuff on Thursday, as well as some nuances about precipitation reactions and solubility of substances and stuff, okay? So I'm going to leave it there. I'm going to give a chance if anybody has any questions. Don't forget, once we close here, we're going to continue. So I'm just going to basically take a break, maybe like a 15-minute break, and we can reconvene at 10 past 7. If you want to, this is an entirely optional activity. You should be able to do the activity on your own by following the instructions in the assignment. But if you want to stick around, I can walk you through some of the calculations, some of the graph making and stuff like that. And this will be experiment P11. P11. It's in your lab manual, but I put in a Word file copy of it in the assignment in case you guys don't have the lab manual with you. All right. So let me see. Are there any questions? Anybody? Any questions? We're good. Either you can open your microphone and ask. Let me know who you are, though. Or you can put a question on your chat box here. Wow. There's a lot of you still in here. Thank you. You guys are awesome. Thank you so much. Okay. Well, I guess nobody has any questions. So I'm not going to end the meeting, okay? I'm going to leave it open. I'm just going to pause the recording here. All right. So let me go back here. Okay, guys, well, if you come up with any questions in the meantime, just put it on the chat room, okay? I'm going to essentially stop my video here. I'm going to mute the phone and just pause the recording, but this will continue on later on, okay? So here we go. Again, if you have any questions, just put them on the chat room.